Hello, my name is Martin Andersek and I'm a senior software engineer at NI. Today I'm going to show you an end-to-end IP data transmission over a physical abstraction layer system consisting of the Core 5G core network, a 5G new radio gNB and a UE simulator. Let me first introduce you to the setup we are using. The demo is based on the physical abstraction layer setup, in short, PAL setup, with higher layer components for the gNB and UE and a simplified 5G core network from a third-party vendor. All machines are connected via 10 gigabit per second network interfaces for the user plane data. For the interoperability testing within Primo 5G, we replaced the simplified 5G core network with the Core 5G core network, and together with them, we made minor changes and adaptations where needed. In detail, the core network consists of the user plane function UPF, the session management function SMF, and the access and mobility management function AMF. The gNB consists of the central unit CU and the distributed unit DU. To enable the end-to-end data transmission, we use a UE simulator at the lower end and a core network machine at the upper end of the stack. In our lab, the setup looks like this. We use 3 machines to serve the aforementioned functions. Let me now demonstrate the IP data transmission in the real system. Here we are logged into all of the machines. This is the core network machine, this is the CU machine, and this is the DU machine, which also runs the UE simulator. Let's first start the core network functions UPF, SMF, and AMF. We can monitor the activity of the core network by checking the AMF log. There we see that the service is loaded. That means we can continue starting the CU and the DU. As soon as the DU is up, we can continue with the UE simulator. There we see that cell 1 is up, and also the core network report that it has found a radio access network node. So let's continue with the UE simulator. It is starting up and it still syncs, and then we can attach it to the network. There we go. We received an IP address, and also the AMF component reports that something has happened. So let's see if with this we can now run any data transmission by first doing a ping to the core network. And we see the ping is successful. So we can continue with the actual data transmission. For this, I will generate UDP traffic from the UE towards the core network machine for the uplink direction, and UDP traffic from the core network machine towards the UE for the downlink. Previous tests with this setup revealed possible data rates of about 1.1 gigabit per second in the downlink and about 240 megabits per second in the uplink. So for this, we have to turn on an iPerf server on the core network to receive the data from the uplink. And there we see we have around 240 megabit per second and only a minimal packet loss. So let's do this now for the opposite direction, for the downlink. Let's first run iPerf as a server. And the client that sends 1.1 gigabit per second. So what we can see here is that on the receiver side, we receive 1.1 gigabit per second, and we have no datagram loss. At the same time, when we switch back to the uplink, we still see a relatively small packet loss. This is because with the 240 megabit per second, we're relatively close to the limit of what this connection permits. If we decrease it a little bit, it would be fine again. In this video, I've demonstrated you an end-to-end IP data transmission over a physical abstraction layer system consisting of the Kumo Core 5G core network and a third-party 5G new radio gNB and UE simulator. Thanks for watching.